So in the second paper, we're going to learn about DeGPT, which tries to optimize decompiler outputs with large language models. So let's welcome our speaker, Pei Wei, from the Chinese Academy of Science.
Thank you. Okay. I'm Pei Wei Hu from the University of Chinese Academy of Sciences. I'm very happy to share our latest research, DeGPT, optimizing the decompiler output with large language model. So first, what is decompilation and why it's so important? As we know, the computer accepts machine code, but it's unreadable for humans. So we write high-level source code and compile it to machine code. The popular compilers include GCC, LLM infrastructure, and so on. But sometimes we want to reverse this process and recover the source code from the binaries. We call this process decompilation. And we use decompilers to decompile. The popular decompilers contain hex arrays of Ada and Ghidra. And decompiling is an important way to understand binaries. It's widely used in binary vulnerability analysis, virus analysis, and software cracking, and so on. Although the decompiler output help reverse engineers to understand binaries, but there's still a gap in readability between the compiler output and the human-written code. The code snapped in the left is the source code for calculating Fibonacci numbers, and the right code snapped is the decompiler output of the binaries. As we can see, there are at least in three aspects, the decompiler output increase the cognitive burdens for understanding. First, the source code contains meaningful variable names. Second, the source code contains comments to help us understand the function. Third, the source code contains more conscious structures, while the decompiler output has redundant variables. And recently, large language model appears with very impressive performance in various fields. It has large number of parameters, which endows it with powerful learning capabilities. What's more, it also trains on abundant code bases, enabling it to cope with different scenarios. As a result, it has a decent ability for rewriting code, even for the unseen code. To boost the optimization of the compiler output by large language model, at least the following two questions need to be properly solved. The first is how to unlock the potential of large language model on our task. As reviewed by previous research, the better way to use large language model is to split your task into different parts and guide the large language model step by step. So we need a proper mechanism to drive large language model to optimize the decompiler output. The second question is how to filter out the gibberish of large language model. As a generative model, large language model tends to have gibberish, which can affect our optimization tasks. So we need a proper mechanism to filter out the gibberish of large language model. First, let's talk about how to unlock the potential of large language model. We break down the task for optimizing decompiler outputs into three steps. The first step is to decide what optimizations to do. The second is how to perform these suggested optimizations. The third is to check whether the optimizations are correct. And we assign these three steps to three roles, which are referee, advisor, and operator, respectively. We call this three-role model. And in general, our framework, DeGPT, is a middleware between the decompiler and the reverse engineers. As you can see, the referee, the raw referee will accept a decompiler output from a decompiler. Then it will ask the large language model for optimization schema. Then the advisor will accept the optimization schema from the referee and ask the large language model for specific rectification methods. The first two roles are based on large language models, and the third role will, which is called operator, will use a program analysis way to filter out the gibberish of large language model. So how can operator filter out the gibberish? Let's think about our task. We want to optimize the decompiler output. We want to improve the readability of it, but we don't want to change the function semantics. So we can filter out the gibberish of large language model by checking the changes of function semantics. If the function semantics remain the same after optimization, we think this is acceptable. And what can represent the function semantics? The current decompilers will generate pursued C code. So for pursued C code, return values and side effects such as global variables, memory values can construct the function semantics. So based on the above observation, we proposed the micro-snap semantic calculation, or MSSC for short, to check the function semantic changes and further filter out the gibberish of large language model. Note that the decompiler output is pursued. We cannot compile it directly, so we use a symbol-based way to simulate the execution of the code. In detail, MSSC will first initialize symbol table for the corresponding code snapped and update the symbol table down the execution passes. After that step, we can get two symbol tables, one for decompiler output, the other for optimized decompiler output. Then we will compare two symbol tables focusing on return values and items that can cause side effects. After comparison, if the corresponding values are the same, we think the function semantics remain the same and we accept the optimization. This is how we filter out the gibberish of large language model. And this page shows a detailed workflow of DeGPT. You can see there are three roles. The first role, referee, will accept the decompiler output from Decompiler and query the large language model for necessary optimizations. And the advisor will accept the optimization schema from the referee, and it will sort the optimizations through the proper prompt for the optimizations and get the specific rectification methods. After that, the operator will invoke MSSC to check the function semantic changes. If the function semantic remains the same, we will accept the optimization. This is the detailed workflow of DeGPT. And this page shows a simple example about the practical performance of DeGPT. The left is the direct decompiler output, while the right is the optimized output. We can see it's obvious the optimized output has more meaningful comments to help us understand the function. It also has more meaningful variable names and more conscious structures. This can obviously decrease the cognitive burdens for reverse engineers when they analyze the binaries. We also evaluate DeGPT on various code bases, including Mira botnet, audio flux, coutils, and LeetCode. We define various metrics for evaluation. For example, we define MVR, which means meaningful variable radio, to evaluate the performance of variable renaming. We also define CR, which means correct comment radio, and NR, which means non-trivial comment radio, to evaluate the performance of comment appending. We define ER, which means effort radio, to evaluate the performance of structure simplification. Also, we have some interesting findings. The first is audio flags appeared later than the large language model's latest training data. However, it has similar performance compared with other code bases. This implies that DeGPT has decent performance on the unseen code bases. And next, we tested DeGPT on both stripped and non-stripped binaries. And we found the stripped symbols mainly affect the semantic-related optimizations, which include variable renaming and comment appending. Third, we found that DeGPT has a high correct rate in appending comments, but not all appended comments are useful or non-trivial. We also do user study on 3 groups of reverse engineers, including professional, intermediate, and basic. We found that participants of all groups show positive attitude to the optimized decompiled output. However, the professional group scored lower than participants in the other group, which reflects the limitations of the knowledge of large language models. This means large language model cannot provide so much knowledge for professionals, but it can do a lot of help for intermediate and basic reverse engineers. So, in summary, we propose DeGPT to leverage large language model to improve the readability of the compiled outputs. It contains a 3-row model to unlock the potential of large language model. It also contains MSSC mechanism to filter out the gibberish of large language model. And DeGPT showed a decent performance on various metrics and the user study. That's all. Thanks for your attention.
Very interesting topic. So let's see if we have questions in this room. We have plenty of time for questions.
I noticed that in the semantics checking process, you mentioned the concept symbol table. Can you elaborate on what does symbol table mean in this process?
Okay.
It's not very clear.
Okay. Because the compile output cannot compile, right? So we use a symbol-based way. At the initialized step, we will extract all the symbols like a variable name and a memory location and a function calls. We do a hash to function calls. We treat this as symbols, and we will assign a random value to them. And for a pair of decompiler output and optimized output, we will use the same random values for the same symbol. And we will update the symbol, the items in the symbol down the static execution passes. And after that, we will check the item values in the symbol table, like that.
Okay, you mentioned variable names, but I think it doesn't affect the semantics, right?
Variable names? Semantic, yeah. I use semantic for 2 meanings. The first is function semantics. It means how this function actually perform like. The second semantic is semantic information for human understanding, like variable names and comments. There is 2 meanings of the semantics. So yeah. So.
Okay, thank you very much.
Thank you.
Thank you. You mentioned the example you gave with the variable name changes. What if you go in and manually change some of the variable names? Does it also consider that if you are looking at some decompiled code and you're going through and changing the variable names yourself? How does it react when you do some variable name changes on your own?
Sorry?
So when you do some variable name changes on your own, in the example you gave, you gave a good example of how it's updating the variable name changes in one of your screenshots there on your code. But what if you go through the decompiled code yourself and then kind of do the variable name changes yourself? Does it consider that as well?
Sorry.
So if you want to go back to a couple of slides here, okay. And hopefully I can point out one of the screenshots that you showed. Keep going. Right there. Yeah, right here. I think you gave me a decompiled output of what your DGPT does.
You mean how do I check the variable values, right?
Yeah, so I think this is like the
They have
decompiler.
different variable names. Do you mean that?
Right, right. What if somebody like myself to say I'm gonna change the variable name and then use your DGPT on top of that?
Yeah. DeGPT will perform various optimizations. We don't perform all optimizations at one step. So there, I said there is a, wait. There is a step in the advisor. First step is sort the optimization. So when you perform variable renaming and structure simplification, they are in the different step, right? And we check the function semantics when performing structure simplification. So in this step, the variable names of this pair, they are the same. Thank you.
So thanks for the talk and very interesting piece of work. So while addition of comments and variable renaming seem to be more intuitive, I was wondering if you could shed more light on the on some example queries to the LLM that you made for structure simplification, because that seems to be more abstract. Like what kind of structure simplification you're looking for? Is it lines of code needs to be minimized and those kind of things? If you could explain.
Sorry, do you mean how do I evaluate the structure simplification? Do you mean the metric?
I mean, what queries to the LLM did you make with regards to the structure of the program and its simplification? Like when we say structure simplification, what exact simplification are we looking for? Lines of code or those kind of things?
You mean what is the specific structure simplification is, right?
Yeah.
We don't do a pre-definition about what a structure simplification do. We just ask a large language model to perform this. So it can do any possible things, and according to my experience, it may remove redundant variables and change the redundant from branch structures, something like that. It's defined by large language models. We didn't pre-define it.
Okay. And in the next slide, I believe when we say the metrics, one more.
Metrics, right?
Yeah. So effort here in structure simplification, that also comes from
That's a good question. That's a good question. So what does this effort mean? This is one metric in hosted metrics. This is a concept in software engineering. And a recent study in ICSE, they do a very interesting experiment. They involve a lot of participants and scan their brain and to decide which metric can actually evaluate the structure complex. And they get their conclusion, the hosted metric is the best metric to evaluate. Yeah, according to that study, we use this. Yeah, that's a good question. Thank you.
Thanks.
We have time.
All right, 2 questions. What kind of context are you feeding into the LLM? Or is it just a single function at a time, or is there other data?
Do you mean what do we send to large language model?
Yes.
It contains 2 parts, promote and the code. The code is changed in different steps. I mean, for example, for the raw referee, it will contain a promote and the original decompiler output. For the advisor, in advisor, it will multiple optimization, right? So, for example, if we are doing the second optimization, its input is a prompt and the code after optimized by the first step, just like that. In general, it contains 2 parts, the prompt and the code snapped. We are going to optimize.
Okay, so you're not providing any, like, for instance, like the call site could be very
we do intro procedure analysis. We don't discuss the inter-procedure things because the token is limited. Thank you.
That's a huge part. And then second question is the types. Do you do anything to try to
types?
To infer like structures, arrays?
That's a very good question. At first, in optimization of the compile outputs, the types is very important, and there are a lot of important research about it. At first, I also want to do it, but let's think about how the previous studies do type optimizations. They will use things like memory layout, something like that. But how can we transfer memory layout to large language models? It's not like text. So I think it will be difficult. But I think if someone can do it, it will be awesome. Thank you.
Thank you. So we don't have more time for other questions, so I have to put all other questions offline. Please find our speaker after this session. So let's thank our speaker, Pei Wei, again.
Thank you.